Hello everyone, welcome to Jnanadipti Academy. In this video, I will bring to you some of the important MCQ on magnetic effects of electric current. So let's start the video. Here is the question. A strong bar magnet is placed vertically above a horizontal wooden board. The magnetic lines of force will be. So here we have a horizontal wooden board, and we have placed vertically one bar magnet. We have placed the north, this is south. So the magnetic field lines, we know that outside the magnet always originates from north and ends in south. So here also originate from north and ends in south. So you can see here the magnetic field lines, they are in all the planes around the magnet, that is on wooden board as well as outside the wooden board. So here option D is the correct answer. The magnetic field lines produced by a bar magnet. So we have a bar magnet. This is north and this is south. The magnetic field lines always originates from north and ends in south. So here the magnetic field lines always originate from north pole and ends in south pole. So option C is the correct answer. Which of the following is not attracted by a magnet? Not attracted by a magnet. So here brass is not attracted by a magnet. The steel, cobalt, nickel, these are all attracted by a magnet, but only the brass will not attracted by magnet. So answer is C, brass. The magnetic field lines. Option A, intersect at right angles to one another. Option B, intersect at an angle of 45 degrees to each other. Option C, do not cross one another. Option D, cross at an angle of 60 degrees to one another. So here we have two magnetic field lines, and two magnetic field lines, they never intersect, they do not cross one another. The properties of magnetic field lines, that they do not cross one another. So here option C is the right answer. The north pole of Earth's magnet is in the option A, geographical south. Option B, geographical east. Option C, geographical west. Option D, geographical north. So here we have Earth, and this is the Earth's north and south. This is the Earth, north and south, and this is the geographical north, and this side geographical south. Okay, now the question is the north pole of Earth's magnet. The north pole of Earth's magnet is in here, it is in south, it is in south, geographical south. So the answer is option A, geographical south is the correct answer. The axis of Earth's magnetic field is inclined with the geographical axis at an angle of about 5 degree, 15 degree, 25 degree, 35 degree. So here we have Earth. This is the Earth's north. This is Earth south. So it is the Earth magnet south. This is the Earth magnet north. Okay. Now the question is the axis of Earth's magnetic field. Earth's magnetic field is inclined with the geographical axis at an angle. See, you can see here the angle. I haven't drawn the Earth magnetic field state. Just I have inclined that one. How much angle it was inclined? It is inclined 15 degree. It is inclined 15 degree. So here option B is the correct answer. The shape of the Earth's magnetic field resembles that of an imaginary. So here the shape of the Earth's magnetic field resembles the bar magnet, the imaginary bar magnet. Option D is the correct answer. A magnet attracts plastics, any metal, aluminium and iron and steel. See, plastics, magnet will not attract the plastics. Any metal, no, not all the metals will attracted by the magnet. Aluminium, okay, but here we have the option D, iron and steel. So it will attract both the iron and steel. So magnet attracts iron and the steel. So option D is the correct answer. A plotting compass is placed near the south pole of a bar magnet. The pointer of plotting compass will. So here we have a bar magnet. This is south, this is north. So plotting compass. So we have kept the plotting compass near the south pole of a bar magnet, and the pointer of compass, it points towards south pole, because the pointer in the compass, it is north pole of compass. So here the answer is point towards the south pole. The pointer point towards the south pole. Option C is the correct answer. The metallic pointer of a plotting compass gets deflected only when it is placed near a bar magnet, because the pointer has option A, electromagnetism, option B, permanent magnetism, option C, induced magnetism, option D, ferromagnetism. So here we have the metallic compass, plotting compass. It always gets deflected when we have kept near the bar magnet. Okay, it will always deflected when we have kept near the bar magnet, right? So here the reason behind why the pointer deflected, because the pointer is a permanent magnetism. It is having permanent magnet. It is a permanent magnet. So that's why it is deflected. So option B is the correct answer. Which of the following statements is incorrect? Is incorrect regarding magnetic field lines? Option A, the direction of magnetic field at a point is taken to be the direction in which the north pole of a magnetic compass needle points. So it is the correct statement. Option B, magnetic field lines are closed curves. Yes, they are the closed curves. Option C, if the magnetic field lines are parallel and equidistant, they represent zero field strength. No, they are not parallel. The magnetic fields are not parallel. So let's see the option D also. Relative strength of magnetic field is shown by the degree of closeness of the field lines. Yes, the strength of the magnetic field can be shown by the degree of closeness of magnetic field line. So here the incorrect statement is option C. So the answer is option C. The strength of the magnetic field between the poles of an electromagnet would be unchanged. If. So here we have a electromagnet. You know that how we will generate the electromagnet. So this is the solenoid coil. Okay, the ends of the solenoid coil is connected to a battery or cell, right? And we have kept a soft iron core inside the solenoid. We have kept a soft iron core, right? Now the question is what? The strength of the magnetic field between the poles of an electromagnet would be unchanged. The strength would be unchanged. So the strength would be unchanged when? Option A, current in the electromagnet winding were double. So if we have double the current in the circuit, the strength is changed, right? The strength of the magnetic field changes. So option A is not the correct answer, right? Let's see the option B. Direction of current in electromagnet winding were reversed. So here if we have changed the direction, now in this one figure the direction of current, it is from the positive terminal. Now if you have changed the direction of current, okay, now if you have changed the direction of current, let's see the current is flowing from this side, that is you have changed the direction of the current. At that time, whatever the magnetic field strength is there in electromagnet, it should not be changed, it will not change. So here this one, the option B is the correct answer, that the direction of the current in electromagnet winding were reversed. The strength of the magnetic field will not change. So let's see option C and D also. Distance between the poles of an electromagnet were doubled. So if we have made the distance double, at that time also the magnetic field strength increases. Now option D is material of the core of electromagnet were changed. So if we have changed the material, in place of soft iron core if we have used steel, so at that time also the strength of the magnetic field changes. So here option B is the only answer, that the direction of current in the electromagnet winding were reversed. At that time only the strength of the magnetic field will not change. So the correct answer is option B. The diagram given below represents magnetic field caused by a current carrying conductor, which is, you see here, this is the diagram they have given. So this is the pattern of the magnetic field. You know that the straight current carrying conductor, the pattern is concentric circle, right? So option A is not the correct answer. And we have option B is solenoid. In solenoid, the magnetic field pattern, you know that one, that is also the not the correct answer. And here we have option C, circular coil. Okay, so circular coil, the pattern is, in a circular coil, the point The point on a circular coil will act as a straight current carrying conductor. So the pattern is concentric circle, and at the center, the pattern of the magnetic field lines, it's uniform straight line. So here this diagram will represent the magnetic field caused by a current carrying circular coil. So option C is the correct answer. The magnetic field inside a long straight solenoid carrying current. So we have here a solenoid, right? And it is connected to the battery or cell. Okay. Now when we pass the electric current, the magnetic field is produced in a solenoid, and the pattern you will get in solenoid that it is similar to the bar magnet. And here inside the solenoid, the magnetic field pattern is same at all the points. That is uniform straight line. Inside the solenoid, uniform straight line. So the answer is same at all the points. So option D is the correct answer. Which of the following correctly describes the magnetic field near a long straight wire? We know that the magnetic field pattern around a long straight wire it's a concentric circle. So here option D, the field consists of a concentric circle centered on the wire. So option D is the correct answer. The north-south polarities of an electromagnet can be found easily by using. So the polarities of north and south can be found easily by using clock phase rule. The direction of current in the coil at one end of an electromagnet is clockwise. This end of the electromagnet will be. So let I tell you the clock rule. So the clock rule, this is the direction of current, that is for the south pole the direction of current is clockwise. Okay, and for the north pole the direction, this is the direction of the current, and it is anti-clockwise. Okay, and it is anti-clockwise. Now look at the question. The direction of current in the coil at one end of an electromagnet is clockwise. So one end is clockwise. It means that is it is the south pole of the electromagnet. So here option C is the correct answer. If the direction of electric current in a solenoid when viewed from a particular end is anti-clockwise, then this end of solenoid will be. Now just now I told you that regarding the clock phase rule. So whenever the direction is anti-clockwise, that end is north pole. So option C is the correct answer. The most suitable material for making the core of an electromagnet is. So the most suitable material for electromagnet is soft iron core. Soft iron core is the most suitable material for making the electromagnet. The magnetic effect of current was discovered by. The magnetic effect of current was discovered by Ncert. Option C, Ncert. A soft iron bar is inserted inside a current carrying solenoid. The magnetic field inside the solenoid. So when we have increased the current in the solenoid, so the magnetic field also increases. Option B is the correct answer. The magnetic field lines in the middle of the current carrying solenoid are circles, spirals, parallel to the axis of the tube, perpendicular to the axis of the tube. So here in the solenoid, the middle of the current carrying solenoid, the magnetic field, it is parallel to the axis of the tube. Already I have explained in the previous question, so just check it once. The front face of a circular wire carrying current behaves like a north pole. The direction of current in this face of the circular wire is, I told you that the north pole. So whenever we wanted to say the north pole, what is the direction of the current? North pole, the direction of the current, it is anti-clockwise. So here we have option C, anti-clockwise. So option C is the correct answer. The back face of a circular loop of wire found to be south magnetic pole. South magnetic pole. The direction of current in this face of the circular loop of wire will be. Just now I told you, whenever south magnetic, what is the direction of the current? South magnetic, what is the direction of the current? That is, it is clockwise. It is clockwise. So here option B, clockwise, is the correct answer. In an electric motor, the direction of current in the coil changes once in each. The direction of current in electric motor, it changes for every half rotation. For every half rotation. Option C is the correct answer. An electron beam enters a magnetic field at right angle to it as shown in the figure. The direction of force acting on the electron, we have to check this one. The direction of force acting on electron beam will be option A, to the left, option B, to the right, option C, into the page, option D, out of the page. Now here we have to apply the Fleming's left hand rule in order to find out the direction of force acting on the electron beam. Alright, so apply the Fleming's left hand rule, you will get the answer, that is into the page. That is, the direction of force acting on electron is into the page. The force experienced by a current carrying conductor placed in a magnetic field is the largest when an angle between conductor and the magnetic field is. See, whenever the conductor is kept in a magnetic field, it displaces. So here the force experienced by a current carrying conductor when we have kept in a magnetic field, it is largest. When it is largest, when we have kept that current carrying conductor 90 degree. We have kept the current carrying conductor 90 degree. The force exerted on a current carrying wire placed in a magnetic field is zero when the angle between the wire and the direction of magnetic field is 45 degree, option B 60 degree, option C 90 degree, option D 180 degree. So the force exerted on a current carrying wire placed in a magnetic is zero when it is kept at an angle 180 degree. Right, so whereas the displacement is maximum when they have kept 90 degree, but 0 when we have kept at 180 degree. So the answer is 180 degree. A current flows in a wire running between the south and north poles of a magnet lying horizontally as shown in below figure. The force on the wire due to the magnet is directed, option A, from north to south, option B, from south to north, option C, vertically downwards, option D, vertically upwards. So here, in order to find out the force on the wire due to the magnet, so here in which direction the wire displaces. So when we have kept the current carrying wire in between the poles south and north, so here it is directed vertically downwards. Vertically downwards. Apply the Fleming's left hand rule, you will get the answer, vertically downwards. An electric motor is a device which transforms electrical energy to mechanical energy. The electric motor transforms electrical energy to mechanical energy. A magnetic field exerts no force on. So the magnetic field will not exert any force on a stationary electric charge. On a stationary electric charge, the magnetic field will not exert any force. Option C is the correct answer. A horizontal wire carries a current as shown in figure below between magnetic poles north and south. So here is the figure. Is the direction of force on the wire due to magnet? Option A, in the direction of current. Option B, vertically downwards. Option C, opposite to the current direction. Option D, vertically upwards. So here, as the current carrying conductor that is kept between the poles of a magnet, so you apply the Fleming's left hand rule, you will get the direction of force on the wire, that is vertically upwards. Option D is the correct answer. A rectangular coil of copper wire is rotated in a magnetic field. The direction of induced current changes once in each half revolution. Once in each half revolution, the direction of the induced current changes. The phenomena of electromagnetic induction is producing induced current in the coil due to relative motion between magnet and the coil. So option C is the correct answer. The device used for producing electric current is its generator. It is the generator that will produce the electric current. Option A is the correct answer. The essential difference between AC generator and the DC generator is. So the essential difference AC and DC generator is, AC generator has slip rings, whereas DC generator has a commutator. So option D is the correct answer. When the switch S is closed in the figure given below, the pointer of the galvanometer moves to the right. This pointer will move to the right when switch S is closed. Okay. Now, if S is kept closed, will the pointer, here when we have closed the switch S, the current is going to flow in the coil. So due to the flow of current, here in the coil, second coil, the galvanometer, it moves towards right. Later, after that, here they are asking that return to zero. Option B, stay over on the right. Option C, move to the left and stay there. Option D, move to and fro until S is open. So here, when continuously switch is closed, after this the galvanometer, when it moves towards the right, after that immediately it will come to the return to zero. Right, it will not stays over the right, it will not come to left, it will come to zero. So option A is the correct answer. Each one of the following changes will increase EMF, that is voltage, in a simple generator except. So option A, increasing the number of turns in the armature coil. Yes, when we increase the number of turns in the armature coil, the EMF increases. Option B, winding the coil on a soft iron armature. Yes, when we have wind this coil on a soft iron armature, the EMF increases. Option C, increasing the size of the gap in which the armature turns. So here, when we have increased the size of gap in the armature turns, at that time the EMF, it does not increases. Okay, now let's see the option D also, increasing the speed of rotation. So when we increase the speed of rotation of the armature coil, at that time also the EMF increases. So here, except which thing, that is increasing the size of the gap in which the armature coil turns. So option C is the correct answer. The north pole of a long bar magnet was pushed slowly into a short solenoid connected to a galvanometer. The magnet was held stationary for a few seconds with the north pole in the middle of the solenoid and then withdrawn rapidly. The maximum deflection of the galvanometer was observed when the magnet was. So here we have one solenoid. Okay, here we have one solenoid, and this is the galvanometer connected to solenoid, and here we have the bar magnet, that is north and the south. Okay, so here when the galvanometer will show the maximum deflection, that we have to find out. Now look at here, option A, moving towards the solenoid. Obviously when the bar magnet moves towards the solenoid, the galvanometer will show the deflection. Okay, now moving into the solenoid, yes, it will show the deflection. At rest inside the solenoid, no, at rest inside the solenoid it does not show. Here maximum deflection will be shown that when moving out of the solenoid. Remember, this is a very important point, very important, that this solenoid, this bar magnet, when you are moving out of the solenoid, the galvanometer will show the maximum deflections. An electric generator converts mechanical energy to electrical energy. Option D is the correct answer. Now, a DC generator is based on the principle of electromagnetic induction. It is based on electromagnetic induction. An induced current is produced when a magnet is moved into a coil. The magnitude of induced current does not depend on We have to find which quantity. So option A, the speed with which the magnet is moved. Yes, of course, when we have moved with the high speed, the induced current is high. And option B, the number of turns of the coil. Okay, the number of turns of the coil If you increase, the current increases. Now, the resistivity of the wire of coil. So here, if you have changed the resistivity, so here we need to find the magnitude of induced current does not depend. It does not depend on the resistivity of the wire. Right, it does not depend on resistivity of the wire. Look at the option D also, the strength of the magnet. Yes, it depends on the strength of the induced current depends on strength of the magnet also, but it does not depend on the resistivity of the wire of coil. So the answer is option C. The frequency of direct current is 0 hertz. The frequency of alternating current supply in India, the frequency of alternating current in India is 50 hertz. At the time of short circuit, the current in the circuit, so at the time of short circuit, the current in the circuit increases heavily. Which one of the following statement is not true? Option A. In a house circuit, lamps are used in parallel. Yes, lamps are used in parallel. Switches, fuses, and circuit breakers should be placed in neutral wire. So here it is not placed with the neutral wire. It should be placed with the live wire. So option B is not correct. So let's check out the option C also. An electric iron has its earth wire connected to the metal case to prevent the user receiving shock. Yes, obviously. Option D. When connecting a 3-core cable to a 13 ampere 3-pin plug, the red wire goes to the live pin. Yes, the red wire goes to the live pin. So option D is also the correct statement. Which is not correct? That is option B. Option B. Switches, fuses, and circuit breakers should be placed in the neutral wire. So option B is not correct. Circuit breaker device which can be used in place of fuse in domestic electric wiring is, in place of fuse you can use MCB, miniature circuit breaker. MCB, miniature circuit breaker. An MCB which cuts off the electricity supply in case of short circuiting or overloading works on. So short circuiting or overloading, the MCB works on magnetic effects of electric current. Option C is the correct answer. So that's it for the important MCQ on magnetic effects of electric current. Thanks for watching Jnanadipti Academy.